When we think about cybersecurity attacks, we usually picture some hacker in a dark room finding a tiny overlooked bug in the code. But what if the vulnerability isn't a mistake at all? What if it's actually part of the original plan? Let's dive into that. So let me ask you this. What if the biggest security risk in your entire application has nothing to do with a coding book? We're talking about a whole category of weaknesses that exist long before a single line of code even gets written. The danger isn't in the execution, it's in the blueprint itself. And this kind of flaw has a name: insecure design. Now, the official OWASP definition talks about missing or ineffective control design. So what does that really mean? Well, think of it this way. It's not that a security lock was built badly, it's that the architect completely forgot to draw a door on the blueprints to begin with. And believe me, this isn't some obscure niche issue. It's consistently a headliner on the OWASP Top 10 list. Now, you might notice it moved from number 4 down to number 6 in the latest update, but don't let that fool you. Its continued presence high up on that list shows that this is a really persistent, fundamental problem, one that's rooted in requirements and architecture, and one that, honestly, a lot of organizations are still struggling with. A huge reason this problem sticks around is that it gets confused with simple coding mistakes all the time. So let's draw a really clear line in the sand here, because getting the difference is absolutely everything. Let's use an analogy here. A regular coding bug, that's like a leaky faucet in your house. Super annoying for sure, but it's a localized problem. You call the plumber, they patch it up, and you're done. But insecure design? Oh, that's a cracked foundation. It compromises the entire structure, and you can't just slap some duct tape on it and call it a day. The whole house is at risk. And this table here really breaks it down. See, insecure design, its root cause is missing controls way back in the planning phase. That means the only real fix is a fundamental redesign. An implementation flaw, on the other hand, is just a coding mistake made during development. You can fix that with a targeted code patch. One is a deep, systemic problem, the other is a localized oops. And this leads to a critical takeaway, one I really want you to remember. You could hire the most brilliant developers on the planet to write the most beautiful, flawless code imaginable. But if they're building on a broken blueprint, the system will always be vulnerable. Perfect implementation cannot fix a flawed design. It just can't. Okay, enough theory. Let's get into the fun stuff. Let's look at how attackers actually exploit these architectural flaws out in the wild. So here's a classic example. An e-commerce site is designed with a fatal assumption. It blindly trusts that the price sent from the customer's web browser is the correct price. The system was just never designed to have its own single source of truth for pricing on the server side. And the attack? It's devastatingly simple. An attacker just intercepts the checkout request before it hits the server. They change the price from, say, $99.99 to just $9.99 and then forward it along. Because the server was never designed to double-check that price against its own database, it just accepts the fraudulent number and happily completes the purchase. Ouch. Or how about this one? Happens all the time. Imagine a multi-step checkout. Add to cart, enter shipping, process payment, confirm order. The design flaw here is just assuming users will follow those steps in order, without any server-side enforcement. An attacker can just skip the payment page entirely and call the final confirmation URL directly, getting the product for free. All because the system never bothered to check if the previous steps were actually completed. Now, these examples are really just symptoms of much deeper issues. When you see teams doing zero-threat modeling, or when security is just an afterthought in the user stories, when you see unsafe workflows with no limits on how often an action can be performed, or when there's this blind trust between different microservices, those are all giant flashing red flags for insecure design. And this gets right back to our core distinction. Having a typo in the code that sets a user's action limit, that's a bug you can fix. But a system where no one ever even thought about designing a limit in the first place, that's the missing door. That's the insecure design. So, if the problem is in the foundation, how do we build a secure one from the get-go? Well, it's all about adopting a proactive mindset. Let's start with the money, because that always gets people's attention. Fixing a design flaw during the planning phase? It's cheap, maybe a few $100 worth of time in meetings and on whiteboards. But finding that exact same flaw after the product is already live in production, that can easily cost over $100,000 in emergency engineering, data recovery, and cleaning up a PR nightmare. The economics here are crystal clear.
The real solution is what we call a shift-left mindset. It's about moving security from the very end of the development cycle to the very beginning. And the most powerful tool we have for this is threat modeling, basically a structured process for thinking like an attacker before you ever build anything.
One of the most common frameworks for this is called STRIDE. Now, it's not about knowing every single attack out there, it's about having a structured way to brainstorm what could go wrong. It makes you ask questions like, hey, could a user pretend to be someone else? Could our data get messed with? Just by going through these categories during the design phase, you start spotting where those crucial security controls are missing.
And the controls you decide to add should be guided by these time-tested principles. Take the principle of least privilege, for example. It's a simple idea. A component should only have the absolute minimum permissions it needs to do its job and nothing more. Or defense in depth, which just means you don't rely on a single firewall, you build multiple overlapping layers of security. These aren't rocket science, but they have to be intentionally designed into the architecture from day one.
Ultimately, this all comes down to a cultural shift. Security requirements can't be some checkbox you tick at the end. A requirement like the user's session data must be protected has to be treated with the exact same importance as the checkout button must be green. It has to be a first-class citizen in the plan.
All right, as we wrap up, let's circle back to the main idea, the one thing I really hope you take away from this explainer. If there is only one thing you remember, let it be this. Perfect code cannot fix an insecure design. If the blueprint is broken, the most talented builders in the world can't make the structure safe. At its core, it is an unpatchable problem.
The only way to solve it is to prevent it from ever happening. You have to design security in from the very beginning. It has to be woven into the requirements, baked into the architecture, and pressure tested with threat modeling. And that leaves us with one final question for you to take back to your own projects. As you build your next feature, ask yourself, are you building on a solid foundation? Or is the blueprint itself the breach just waiting to happen?